7 million years ago, one of our ancestors attempted something that should have failed. It raised its body above the ground, balanced its weight on only 2 limbs, and took an uncertain step. That movement made it easier to fall. It exposed the body to predators. It placed new pressure on the spine, hips, knees, and feet, and yet the experiment did not disappear. Its descendants kept standing, kept walking, and eventually changed the planet. So, why would evolution preserve such a dangerous way of moving? The answer is hidden inside an ancient forest, a collection of broken bones, and a trail of footprints, preserved by volcanic ash. And by the end of this journey, an ordinary walk across your room may never feel ordinary again. Imagine Africa millions of years before cities, roads, farms, or even the earliest members of our own genus. This was not one endless grassland. Woodlands, rivers, patches of open ground, wetlands, and dense vegetation formed an enormous living puzzle. Food appeared in one place and vanished from another. Predators waited below. Valuable fruit hung at the edges of thin branches. Somewhere inside that world lived a creature unlike any species alive today. It could climb. It could grasp branches with powerful hands and feet. It could move on 4 limbs. But under certain conditions, it raised its body and moved upright. That behavior appeared surprisingly early. Large brains came later. Complex tools came later. Controlled fire, symbolic art, agriculture, and civilization came much later. Walking upright was not the reward at the end of human evolution. It was one of, but here is where the mystery begins. At first, 2 legs seem worse than 4. Watch a leopard accelerate. Its body remains low, stable, and supported at 4 points. Watch a chimpanzee charge across the ground. 4 limbs help it generate power, while keeping its weight close to the surface. Now, picture a human. A tall, heavy body is balanced over 2 relatively small feet. The center of mass rises far above the ground. Every step becomes a tiny act of danger. In fact, walking is a controlled fall. You lean forward. Your body begins to drop. One leg swings ahead and catches you before you hit the ground. Then you repeat the same sequence with the other leg. You perform this calculation thousands of times without consciously thinking about it. But one misplaced stone can expose the weakness of the entire system. Our vertical spine must support weight in a way that can contribute to pain and injury. Our knees repeatedly absorb impact. Our ankles must balance the body on uneven surfaces. Our feet must remain flexible enough to soften each landing, then become rigid enough to push us forward. Even reproduction became caught inside this evolutionary compromise. The human pelvis must support upright walking, while also allowing childbirth. It performs both tasks, but neither one without difficulty. So why did natural selection not abandon the experiment? Because evolution does not begin with a blank page. It cannot throw away an ancestral body and construct a perfect walking machine. It modifies structures that already exist, bone by bone, muscle by muscle, generation by generation. The opening beneath the skull shifted into a position that allowed the head to balance above the spine. The spine developed curves that kept the upper body closer to the center of support. The pelvis became shorter and broader. The thigh bones angled inward, bringing the knees beneath the body. The feet gradually became more effective at supporting weight and pushing against the ground. But these features did not appear together in one dramatic transformation. That is our first major clue. Bipedalism was not a single invention. It was a long series of experiments. Some early hominins could move upright while still possessing powerful climbing adaptations. Others probably walked regularly, but not exactly like modern humans. Several species may have developed different solutions to the same balance problem. Human evolution was not a straight line of figures marching from crouching ape to modern person. It was a branching maze filled with bodies that climbed, walked, balanced, and moved in ways that no living species perfectly reproduces. For a long time, however, one explanation seemed to solve everything. The African climate became drier. Forests shrank. Grasslands expanded. Our ancestors, descended from the trees, entered the open savanna and stood upright to see over tall grass. Picture the scene. A small ancestral ape rises above a golden sea of vegetation. Far away, the grass moves. Is it another member of the group or a hungry cat? Standing provides the answer. It is a memorable image. It appears logical, and it may describe one useful advantage of upright posture. But it cannot explain the beginning of the story by itself. The fossils do not place every early biped in an endless open grassland. Some of the oldest evidence comes from environments containing trees, woodland, river margins, and mixed vegetation. Then, Scientists examined Ardipithecus ramidus, a hominin that lived about 4.4 million years ago. Its body looked like an evolutionary contradiction. Its grasping big toe could help it move through trees, yet parts of its pelvis suggest that it was also capable of upright movement. The environment around it was not simply a treeless savanna. Now, the investigation must leave the grass and climb back into the canopy. Picture an ancestral ape standing on a thick branch. One hand grips an overhead support. Both feet press downward. The free hand reaches toward fruit growing just beyond the safest part of the tree. In this position, standing upright can provide an advantage. The body can reach farther. The animal can use one hand to gather food while the other stabilizes it. It can shift its weight across flexible branches without hanging the entire body beneath them. Living apes occasionally use upright postures in comparable situations. They are not habitual human-like bipeds, but they demonstrate that standing can be useful long before an animal commits completely to life on the ground. And that changes the central question. Perhaps our ancestors did not first stand because the forest disappeared. Perhaps part of the behavior developed while they were still living inside it. But that is only half the answer. An occasional posture on a branch does not automatically explain why natural selection would eventually rebuild much of the skeleton for regular terrestrial walking. Something had to reward the individuals who use two legs more frequently. One possible reward was food. Standing can extend an animal's reach toward high branches or low shrubs. Instead of repositioning the entire body, an individual can rise, collect several items, and use its hands while the legs provide support. Once those hands are no longer required for every movement, they can also hold what the animal collects. Imagine finding fruit in a dangerous location. Eating everything immediately may attract competitors, but an individual capable of gathering several pieces and carrying them toward cover can reduce the risks. Food could be transported to offspring. It could be shared with allies. It could be protected from rivals. The advantage does not need to look revolutionary. A slightly greater chance of survival, repeated across thousands of generations, can transform a species. This is where one of the most famous explanations enters the story. So, humans stood up to free their hands for tools. It sounds convincing, but the timing creates a problem. Evidence for bipedal adaptations appears millions of years before the widespread stone tool traditions normally associated with later hominins. Free hands eventually became extremely important, but advanced tool-making probably was not the original reason the first ancestors stood upright. The hands may have been released first. Only later did evolution discover everything those hands could do. But food and free hands still do not explain the entire body. Another clue comes from energy. Chimpanzees can walk on two legs, but they usually keep their hips and knees bent. Their muscles must work hard to support this posture. Human legs are arranged differently. They can swing beneath the body more like pendulums. Each step recycles movement instead of requiring the muscles to lift and stabilize the body in the same way. The heel meets the ground. Weight moves forward. The arch changes shape. The toes push the body onward. For an animal moving between scattered food sources, this efficiency matters. Saving a tiny amount of energy during one journey changes almost nothing. Saving energy during every journey, every dry season, and every generation can become a powerful advantage. Yet efficient long-distance walking may have been a later improvement rather than the first cause. The earliest bipeds did not possess exactly the same long legs, stiff feet, and extended stride as modern humans. Their bodies were mixtures, capable on the ground, but still connected to a life involving trees. Then, Africa's changing climate added another possible reward. Imagine the midday sun striking two animals. One keeps its torso horizontal. A large area of its back faces the sunlight. The other stands vertically. Less of its body directly faces the overhead sun, while its chest and head rise into moving air above the hottest layer near the ground. In exposed environments, upright posture may have helped reduce heat gain and improve cooling. But once again, this probably was not the entire original explanation. Early bipedal behavior existed in habitats containing trees. Heat may have strengthened a behavior that had begun for different reasons. Evolution does this constantly. A feature can emerge in one context and become valuable in another. Feathers may have influenced temperature control before they enabled powered flight. A structure does not remain permanently attached to its first function. Upright posture also raises the head. From above broken vegetation, an individual can locate distant trees, recognize other group members, search for water, or notice a predator sooner. But this advantage contains its own contradiction. Standing makes it easier to see. It also makes the animal easier to see. A predator hidden in the grass may suddenly notice the upright silhouette. Detecting danger helps only if the individual can respond before the predator attacks. So, why did the behavior persist? Because evolution does not require perfection. It requires the total benefits to outweigh the total costs under particular conditions. And those conditions never stopped changing. About 3.6 million years ago, several hominins crossed wet volcanic ash at Laetoli in what is now Tanzania. Their feet pressed into the surface. More ash later covered the tracks, and time transformed them into stone. Millions of years passed. Then the footsteps returned to the light. The Laetoli Trail includes roughly 70 early human footprints, extending for almost 27 meters. They were most likely produced by Australopithecus afarensis, or a closely related hominin. Bones tell us what a body may have been capable of doing. Footprints record behavior that actually happened. A heel came down. Weight moved over the foot. Toes left the surface. Another step followed. But even these footprints do not reveal one universal walking style. Evidence from ancient trackways indicates that different hominins may have shared landscapes while using distinct forms of bipedal locomotion. The road toward modern walking was crowded. It was experimental, and it was nothing like the clean evolutionary parade shown in old illustrations. Over time, some members of the human lineage developed longer legs, stronger arches, and increasingly effective terrestrial strides. They could travel farther between resources. They could carry food over longer distances. They could transport infants and useful materials without sacrificing every step. The consequences began multiplying. Free hands could gather. They could carry. Eventually, they could shape stone, control weapons, transport fuel, and move resources back to a social group. Walking upright did not automatically create intelligence, language, or civilization. It changed the opportunities available to natural selection. And this is the real twist. Bipedalism mattered, not because it solved one problem, but because it created a platform from which many other adaptations could become more useful. Efficient travel expanded the territory an individual could explore. Free hands expanded what it could transport. Greater manual control expanded what it could create. Social cooperation expanded how food, tools, and knowledge could move between individuals. Standing upright changed more than the direction of the spine. It changed what our ancestors could carry into the future. But the transformation left us with a bill. Our backs remain vulnerable. Our knees wear down. Our ankles twist. Our feet develop painful problems. The structure of the human hip reflects adaptations to upright locomotion that can also contribute to characteristic vulnerabilities. We are not a perfectly engineered final product. We are a living compromise. Every time you balance on one leg during a step, muscles across your body stabilize a system assembled through millions of years of change. Every time your heel touches the ground and your weight rolls toward the toes, your foot repeats an ancient mechanical sequence. So why do humans walk upright? Not because of one predator, not because of one tool, and not simply because the grass became tall. Our ancestors probably possessed a flexible collection of climbing, standing, and walking behaviors. Upright posture may have helped them balance, feed, and reach while still using trees. As their environments and lifestyles changed, the same behavior gained new advantages on the ground. It helped them carry. It extended their reach. It may have improved travel efficiency. It may have reduced heat exposure. It changed what their hands were available to do. Different advantages mattered at different times. Each one reinforced a behavior that already existed. Gradually, an occasional posture became more frequent locomotion. Frequent locomotion changed the skeleton. The changing skeleton made new behaviors possible. There was never one morning when an ape stood up and became human. There was a chain reaction. First came flexibility. Then came opportunity. Then came commitment. And commitment opened evolutionary doors. No ancestor could possibly have imagined. One uncertain step did not complete humanity. It made much of what followed possible. The next time you cross a room, notice how ordinary the movement feels. Your body leans, falls, balances, and catches itself without asking for your attention. But hidden inside each step is an experiment that began millions of years before anyone existed to remember it. You are not simply walking forward. You are repeating one of the oldest surviving stories written inside the human body. And upright walking is only one chapter. Our hands, shoulders, voices, brains, and social instincts each contain another mystery waiting to be uncovered. Which one should we investigate next? Share your answer in the comments. Subscribe for the next journey into our prehistoric past. And remember, the most familiar parts of your body often hide the oldest secrets.